Alright, hello everybody. Welcome to one of these folding things. Well, not folding, this mathematical pattern, geometry of pattern things. I did this one yesterday, but my battery ran out, so I couldn't save it. And my battery ran out, so I don't even know where it stopped. But I was using this timer yesterday, and it turns out that it doesn't work. So I'm not going to use it today. I know what time it is, so I'm going to be looking at the clock and see and gazing myself. So I'm going to erase all this. And so today we're going to go over the star angle list, and if time allows, we'll also go into some solids. But I think this is very important because usually when they do the mathematical analysis for geometric patterns, whether they be Islamic or otherwise, it's usually done with degrees. And I am a strong what's the word? Not advisor, I'm a strong advocate for the radians method over degrees. Much better to use radians than degrees. That's what I say. But what do I know? So I'm going to make a case for it. I should shave, I should cut my hair, yeah, but, well, I don't like to, so here we are. Okay, so we're going to start with, well, what are we going to start with? Yeah, well, we're going to start with, we saw these before. By the way, nobody asked for this lessons. I should maybe charge for these. I'm giving them away because I'm obsessed with death and I think that I'm going to die soon, and if I don't put this out somehow, somewhere, then, you know, what's it going to be? Maybe it's a little morose thinking, but it is kind of true. Either I do this or I don't, right? So I'm just going to do it. Nobody asked for this, so I'm sorry if this bothers you. You don't have to watch it if you don't like it. If you do like it, then welcome. Feel free, if, welcome, yeah, right on. So, you know, if you've been paying attention and following these lessons, and you might have been here yesterday, I don't know, hopefully yes, hopefully don't, I will see. This is the sum of this is the internal angle formula. This is the internal angle for a regular polygon. So the internal angle for, dude, my handwriting, for a regular polygon. Internal angle for a formula. All right. So, all right, we just, just a little recap of this, right? So we're saying that if we have, well, first off. What if we put in, let's do a little list. So which numbers can we plug into this thing? Well, if we put in 1 minus 2, well, it's a no-go. If you write 2 minus 2, that'll be like 0 pi, it's a 0, over 2, so that's equal to 0, so, 2, no. What if we put in 3? So if we plug in 3 into this formula, it would be like 3 minus 2 times pi over 3. We're plugging in 3 here. It's like function of 3, I guess. Function of n, putting 3 in there. I don't know, maybe mathematics. So this is equal to pi over 3, right? So we're saying that in an equilateral triangle, this angle is going to be pi over 3. And this is built upon, we saw this the last couple of classes, right? But we always have to go over these things. Any triangle is equal to pi. So the sum of these three, whatever they are, they could be different. They could be the same. Sum of 2 could be the same. 1 could be different. But the sum of them will always be equal to pi. The sum of the angles will be equal to pi no matter what triangle you're working with. What's interesting is how this works in the case for just regular polygons, for polygons themselves. I mean, if we just take away this, and take away this, and leave that in there, take away that, and suddenly we have the sum of the internal angle formula. So now this is the sum of the angle formula for a polygon. What? Yeah, no, maybe this classes are a mistake, man. Maybe I really am very disorganized. Sum of the internal angle. Dude, this is the worst. Some of the internal angle, some of the internal angles of a polygon. Formula. This thing right here. So that is to say that if we have any pentagon like that, and we from a point connect outward to any, we see that it draws in 1, 2, and 3 triangles. So then the sum of these angles, so this angle plus this angle plus that angle plus this angle plus this angle is going to be equal to 3 pi. This pentagon can have any shape. These vertices could be placed anywhere in space. And as long as we can map them out, the sum of the angles will always be equal to 3 pi. That's kind of cool, I think, because we just have to keep this in mind, and this will always work out for us. So, right, radians over degrees, right? We're looking at that. So we saw the other angle formula for the regular polygons, where it kind of goes like this, and then over n, and then that's how we get the internal angle formula for a polygon. So what I want to do, and this is kind of crazy because I've only done this a couple times, but it really helped me understand something. We're going to do this little list, and we did this yesterday, so again, I should not mention that because it's like it doesn't exist. And here I'm going to write in like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. I wanted to get up to, well, yeah, 12 is an important point to get to, but I think I need a little more, maybe lift them up a little bit more. We're learning, you guys, we're learning. And well, yeah, I'm going to build on what we said yesterday, but I'm going to try and explain it better. And then from here, we're going to go, what was it? Here we're going to write n minus 2. We're going to write n minus 4. We're going to write n minus 6, n minus 8, and n minus 10. So, you know, it goes on and on and on. This right here can also be written as the internal angle for the polygon itself. So this is like, we're saying it like this. This one is, we're saying it like this. This one can be expressed like this. This one like this. And this one like this. So as you can see, this number that we're subtracting n by is double of whatever, well, this one technically like this. So remember that star system we talked about with the dashes? So if I say to you 5-4 like this, that means that we have 5 points and we jump 2 vertices to draw a line. So it would be like this one. So we could even like find, so this is a very common, like this is the first star pattern for real. It goes like this. And that it would be like these 5 points. And it goes 0, 1, 2, and there's the line. 5, 2, 5 points, 2 vertices, right? System repeats, ends up, you know, completing into this little system. And so if we look at this angle, so if we wanted to find, you know, what this angle is right there, we go like this, and then we put the n underneath. So this angle is going to be 1 pi, or rather just pi maybe, pi over 5. n minus 4, n is 5, and that multiplies by pi, and that we put in over n. That was the internal angle formula thing. So this is like n minus 2k over n. Because this is k number. Well, this is this number represents here, that's the k, because this is written in the form of n dash k. And so the formula for the angle of a star is n minus 2k over n. So depending on how many points you jump, you multiply that number times 2, and then subtract that from n and over n, and that'll give you the internal angle for a polygon, for any star. So this is a little something I came up with, but it's true, you know, it holds up. So n minus 2k, so this is the internal angle for a star formula. I like this better, internal angle for a star. What's cool is that you may also, well, this n minus 2k times pi, of course. This I discovered yesterday while going over the list. I actually like, wait a minute, 1 times 2 is 2, 2 times 2 is 4, 3 times, like, wait a minute, I see a pattern here. And it turns out that, yeah, this is the formula for it. So you can use this formula to get the internal angle of any star, which I think is pretty cool. So let's do a little list, and it's going to be like a little metaphysical list. Because we can think of, well, why did I put 0 there, man? 0 should not be. N equals 0, that's nothing. Just a reminder, these numbers represent points on a circle, equidistant points on circles. I don't know why I'm doing this. I really have no idea, other than I don't know if I'm a narcissist or I'm just so excited about these things. I hope it's passion and not some weird fucking psychological disorder. It could be a combination. We're 10 minutes in, so it's not that bad. So if I say N1, it's 1 point, but it's evenly spaced to itself. So that's pretty much that. Like, so 1, this is N1, right? If we say N2, then it becomes this, right? And we can actually connect these 2 points. We would go like simply, where's the other marker? If we simply go now 0, 1 and draw a line. So we could say that that line can be described as 2-1, or simply just 2. By the way, these squigglies are brackets, which I suck, like terribly suck at drawing them. That's better. It's better, but still. So these two are equal, but so this line is that, right? All right. And you know, we could keep going, making this go up. So instead of 2 points, we could write in 3 points. Instead of 2 points, we can write in 4 points. Right? Simply doubling that. And we can draw like a little system where if we kind of go like 0, 1, 0, 1, 0, 1, 0, 1, we get a square. So we could say that, you know, 4/1 is the square. So because 4/1 is simply 4, the polygon itself, we always write it as simply 4. By the way, most people do not use the brackets anymore. Like, it's just an antiquated thing. It's like 19th century stuff. So we don't use the brackets anymore. You won't find the brackets anymore. But I like to use the brackets because why not, right? I guess I'm a sucker for certain things. But people just write 4. Like 4, you understand that's a square. But so if we write in, what if we change this little system and we kind of count now to 2? So we go like 0, 1, 2, and then we go, and well, that closes, and then we go 0, 1, and then here 2, and then that closes there. So these two lines can be described as 4-2 because they're closed systems. And what we can see also, so we can see here the way that this is made up of 2 of the lines we saw before. So we can take the denominator out of the equation of this, put it outside of the brackets. That's also why I prefer the bracket, because it allows you to sort of contain the shapes. We take it and we leave that thing inside of there so we can understand that this system of 2 lines that go like this are made up of 2 2's. So a 2, by the way, is simply just a line that goes through the center. So a diameter is 2. Okay? So let's go ahead and just write this list. Alright. So, as we said, 1 makes no sense. We can't subtract 1 from 2, so we don't write anything. 2 minus 2, well, that's 0. 3 minus 2, that's 1. 4 minus 2, that's 2. We can see a pattern. It's simply going to count down. 3, 4, 5, 6, 7, 8, 9, and 10. And then we go now for the other column here. So 2 minus 4 makes no sense. 3 minus 4 cannot. 4 minus 4, and we get 0. So here at the level of 2, we're in 0. 5 minus 4, that's 1. And we can see a pattern. It's going to start counting down again. 2, 3, 4, 5, 6, 7, 8, and you know, on and on and on. Now 6, we start here at 6 where this 2 is, so here, and then we write in here this is going to be a 0, 1, 2, 3, 4, 5, 6. We go to 2, we should start with 0, 1, 2, 3, and 4. We go to 2, we start with a 0, 0, 1, and 2. So it kind of has this like, you know, descending aspect of it. The way that I think about it, you know, metaphysically, is that 0, well, we said that that's just simply a line. So whenever a 0 appears, it's basically just a star line that goes through the center. So 0 is just half a term. So that's pi. So whenever 0 appears, that's pi itself. So metaphysically, 1 is the ultimate being. It's indescribable. It's only understood by itself, almost. We can almost like look at it, but we can't describe it properly, I guess. I guess it could be like the imagination, the 1. And then 2, that's sort of like the price to be, but it negates itself. It's sort of, you know, just flat. But then when 3 comes into the game, that's when something happens. So the first polygon is the 3, and we can see here that that's sort of where the case is. So, you know, this is where the first case is, and then second case, we start here. Third case, we start at the 7, actually, right there. So it kind of goes like 1, 4, 7, and then 9, and then 11, kind of just like does a little jump around. Actually, no, 4 has a 1, it's 5. 5 has a 1. So it's like every odd number has a new star born. 3, 5, 7, 9, 11. So a new star is born every time on those. Alright, so what do these numbers mean? Well, those are the numbers that pertain to the angles. So, you know, like these numbers actually represent which star we're working on. So we could just pick one at random. So let's look, I don't know, let's look at this one. What does this mean? That means that the star for the 9, 2, so 9, 2 like that, the angle of that star, right off the bat, we know that it's going to be 5 pi over 9. Right off the bat, we know that. You know, 5, that's that number, times pi over n. So this right here, this result, is what we're getting here. So we're constructing this number, n minus 2k is this list. And so that will give us what we multiply by pi and what we put over the n number of what it's sort of like the polygon that spawns it. Interesting enough, these, you know, multiply by pi, so several patterns actually occur, and they're pretty mystical in a certain way, but it's interesting that we can just quickly gather an angle from any configuration. So let's like look at the star for that one, just because it's also a nice continual star. So let's just draw in these points. So the way I draw my polygons by hand is I draw, so 9 is going to be, you know, 3 points first, and then I'm going to imagine a circle. I'm going to imagine a circle, I'm going to draw in 2 points in between these, and that'll give me 9 points. So 9, 2, I got to jump in 2 vertices every 2 points, so 0, 1, 2, 0, 1, 2, 1, 2, da. Like that. So what we're saying, you know, within this scheme, is that this angle right there, that angle is 5 pi over 9. This angle right there, of this star. 5 pi over 9, we're regular, of course. And I think that's pretty cool, because it's just a very fast way of getting your, what angle your star is at. So if you look at an Islamic pattern, like the one I have there pasted on the board, right beside the board there, we could use this system and like gather all the angles that we need. And, you know, just by looking at how many vertices a shape might have, if it's concave, no, not concave, convex, what is that? No, if it's just like not sinking anywhere, so we could just like understand it to be a polygon. We could apply these methods and find whatever we want. And so, you know, I think it's pretty cool. It gives for a very beautiful analysis of patterns in general. So, awesome. We got, this is going to be the n minus 2k line, so this is the n minus 2, and this is the k. So this sort of like which column is what k it is, right? So first column k1, second column k2, k3, k4, and k5. And that's how many subtractions we take from n, so of course, you know, it goes like that. I think this is very beautiful. Honestly, like I'm always in awe of this. But let's analyze some patterns now. So what time is it? We're 20 minutes in. So I'm gonna take away some of these just to get away from it. You should do it yourself at home. I think this is a very beautiful list to have. And because we're gonna look at an 8 and a 12, I'm only gonna keep the information for the 8 and 12. No, you know what? Let's do the 7 we did last time. So let's do an 8 and 7. So we're going to take away everything that's not 8 and 7. So I don't know if this is, I don't know if you guys can see well, if it's too dark. If it's too weird, I don't know if you guys just wait for this. I don't know if you're liking it at all, but again, nobody asked for this thing, so. Anyway, these are the two patterns we're going to analyze right now, using this little system. So we only care about these two right now, 7 and 8. These are 7-fold and 8-fold patterns. So everything else we're just going to do away for now. So 7, you take away the 6. And we're going to do these two. Okay, so let's look at this one first. This one, this star right there is a 7-2. We can sort of look at it. So I construct my arbitrary 7 points, and I can then connect them 0, 1, 2, 0, 1, 2. So this star is this star. So we know that it's this star, and then it has like a little hexagon there, that comes out of it. Kind of like this, and then like this. Kind of like that, right? So what we want to do is we're going to find this angle, we're going to find the angle of this, of all of them. We're going to find all the angles of all the shapes. Pretty much that's what we're trying to do. So because in the Islamic pattern tradition, these lines tend to go out like this, like a line will flow onward, they're always complementary. There's always going to be a straight line, so whatever angle we find, the remainder of it will add up to pi, to 180 degrees. So what is this? So if we're saying that this is an 8, 2, this angle right there, that's a 3 pi over 7. And then because it has to add up to pi to form a full line, this is going to be 4 pi over 7, this angle right here. And because it's complementary, this one is also going to be 4. And further, if we actually evaluate it, like at there, we keep the cross going. So, okay, I'm going to do this little thing now. I'm going to show you how, if we add these 4 numbers up, we're going to get double of whatever base number we work with, because a full turn is going to be 2 pi. So if we add 4, 7, 3 and 4, that's 7, 3 and 4, that's 7. So 14 over 7, that's 2. So 14 pi over 7 is equal to 2 pi. What this means is that at any point in our pattern, it's always going to add up to 14. Whatever number we put into the angle has to add up to 14 around that point. That's like the rule. So instead of writing this, I'm just going to write the number down. So I'm going to take away this, I'm going to take away this too. Take away these. And leave that there for now. I'm only going to write in the number. So again, it has to add up. So 4, 3, 4. Ah, damn, I hope you guys can see that. So 3, 3, 4, 4. Alright, cool. And now what this angle is, has to do with this one. Because if we keep these lines going, you're going to see that what we're doing is we're constructing a regular heptagon. So this angle is this one. So here we have a 5. So that means that because it's complementary, this one is also a 5. It's mirrored, so here's going to be a 4. And then what happens is, well, let's look at it. This one seems to be the case for a more mirrored case. So over here, there's also going to be another star, so it's going to be a 3. This one's going to be a 3 as well, which means that over here, there's also going to be a 3. Which means that here is going to be a 4, because it kind of like complements itself. So 4, 4, 5, 4. So what are these two? Well, actually we kind of know, because it's also going to be inside, so that's a 5. And over here, that's a 5. And well, we have 1, 2, 3, 4, 5. Was it a pentagon? No, it's a hexagon. 1, 2, 3, 4, 5, 6 points on this shape. I'm just going to draw a very crude version of it. Let's just say that it's like that. That it looks that this shape right there, this shape right here, is this one. Let's just say. Now, because there's 6 points, so 1, 2, 3, 4, 5, and 6, the sum of the angles has to be equal to 4 pi. Now, we're working with base 7. So we have to get this out of a base 7. So what is 4 pi when we're base 7? So we multiply 7 times 4, that's 28. So that's 28 pi over 7 is equal to 4 pi. Which means that the sum of these angles have to add up to 28. So we have some clues here. We have a 5 here, have a 4, 4, then 5, 5, and 4. Let's add them up. So 3 5, that's 15. And then we have 3 4s, that's 12. Okay, we're missing one angle, so one of these is off. That's on me. So I guess that this one is also 5 in it. Because it goes... Oh man, I should write it down here. So this is 3, 3, it's a 4, 5, 4. That was a 5, man. No, it makes no sense. Wait a minute. That is a 4. And over here, that's a 4 as well. That's a 5. And over here, that's a 4. Oh man. So this is wrong. And so that means that these are wrong. So maybe I should write it down. I'm going to draw it again. Let's do this one more time. Well, this time I'm going to use sort of like the advantage I have of knowing a little bit of what's happening, and I can see that's one star after another. So I'm pretty much just going to go with this flow. And so this is going to be a point, and over here is going to be a point. So 1, 2, 3, 4, 5, 6, and 7. If I'm mistaken, 1, 2, 3, 4, 5, 6, 7. All right. So there it goes like this. There it goes here, 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 here. I guess here, there, here, there, here, there, here. Badly drawn, but I guess I'm sort of getting the idea for this. And this one kind of goes here, and then this one kind of meets there. All right, so we're saying that again. So this one's 3, so that means that this one's 4, this one's 5, which means that this one's 5. Again, 3, so this one's 4. 5, 4, and what are we missing there? So 4, 4, that's 12. And 5, 5, that's 10, so 22. And we said we wanted to get to 28, so we're missing 6, so that means that this one is actually 6. Makes more sense. So this hexagon shape that we're looking for, whatever, has these configurations. These are the angles of this hexagon shape. Whatever these hexagon shapes are. And because they're always complementary, we can always find, like, we can keep filling in the rest of the information. As long as we can find, like, all right, well, this is 3 and this is 3. By the way, if you're asking why this is 5, it's because inside of the star is the other star. So whenever you select a star, you can always find the one before it inside. So that we have there, it's a regular heptagon. Regular heptagon is n-1, so that's 5 pi. So that's where the 5 goes. Here's where the 3 goes. And so you might notice that we don't have 6 pi over 7 in this list, and we don't have 4 pi over 7 either. We're focusing on the 7. For the stars, we only have 5, 3, and 1. So 5 pi over 7, 3 pi over 7, and pi over 7 are the angles of the stars for 7. But here we clearly see that the angles that are forming are like, we can find them rationally within the 7 system, but they're not here. So what we do in those cases is actually understand to be of a double. So for instance, this 6 pi over 7 that we have there, if we multiply by 2, like the whole thing is multiplied by 2, we're going to get, 6 times 2, that's 12. 12 pi over 14. So by also just getting the angle, we know which star it's going to be. Because we see that 12 and 14, well, 12 is 2 minus 14. So that means that this is the internal angle of a tetradecagon, a 14gon. This angle right there is sort of like what happens when you write in this just a 14. So the angle of a 14 is this. So that means that this angle right there, this angle that these two come in, is the internal angle of a tetradecagon, which I think is pretty cool. And then this 4 pi over 7, if we also multiply that by 2, so 4 pi over 7, we multiply that by 2, we get 8 over 14, 8 pi over 14. So 8 is, how many times minus 14? Well, we can also see like it goes, 10, 12, 8, so that's here. So this star is the 14, 3. So this angle pertains to the 14, 3, which is present right there. Wow, that's the worst one I've heard. That recording right there, wow, that sucks. Hey, I might suck, but that's not as bad as that. Wow, vato. Pases. Que falta de respeto. Andar caminando por ahí con esos ruidos, güey. Bueno, mínimo es tan mal como el DF, güey. La neta, eso se pasan de lanza. Alright, so we looked at a 7, we broke down this piece. And well, if I were to add something else, it would just be to find which ones of these. So let's just look at it once more, I'm sorry. So we cracked the angle, so we said this one was, I'm going to write them outside now. 6, 5, this one was, we have 3 4s, so it has to go like this. So 6, 6, 4, 4, 5, 5, and 4, if I'm not mistaken. Yeah, seems to work. And then just to be really sure, we know the angles. We just have to be sure of which of these are the same. So just to be clear what I mean, these 4 are the same, and these 2 are different, but they're the same amongst themselves. So these, we could put in a circle here, and these retain to like a circle, right? These are the same lines. So this line and this line are the same. This line and this line are the same to each other. And then these 2 are different from them, but these 2 are the same. So that kind of like leaves us with a very interesting proposition, that if we just made these angles and then just made sure that this value stays, retains, then the shape is automatically formed. So I think that's a cool way to play around, and also like to think, well, if I want to build a hexagon with base 7, right, which angles do I have to come up with? And so I think that's pretty cool, that we just, automatically we have the angles. 6 pi over 7, 4 pi over 7, 5 pi over 7, 4 pi over 7, 5 pi, 4 pi over 7. So I think that's cool. Now, let's look at this pattern right here. How long we got? Alright, we're about 40 minutes in, so that's a long time. So I'm gonna just finish that one off, and then we'll see what else happens tomorrow. So we're just gonna look at these now. Alright, so I have the sort of thing of foresight for that one. I know that this star is 8-3. I know because I folded it and whatnot, but let's just pretend that I know. Let's just say that we know that that's an 8-3. So sort of what's happening here would be like, that's a very, very bad 8-3, man. So bad. Yeah, don't judge me. I'm better with folding than I'm with drawing. So we're saying that that's happening, and then after these petals, or these star shapes, whatever they are, the kites, then these petals come up. These little hexagon petals. So what are we talking about for these petals? So we want to crack them now. All right. Well, first things first. So we say that the angle that comes out of there, this angle right here, is equal to the octagon itself. And well, how do we know that? All right, let's stick to what we know, I guess. It's always difficult to choose where the starting point of your analysis, because then you have to take certain things for granted sometimes, but anyway, it doesn't matter. This is an 8-3. So this point right there, that's 2. And we're in base 8. Right? N is 8. So that means that we have to add up to 16. The full circle is going to add up to 16. So we have 2. The angle's complementary. because it's, you see that that's a straight line. Straight lines are 8, right? Straight line. So that's going to be 6. This one is a star underneath the A3. So we go from here to here. So this point is going to be a 4 as it comes in with this one. So there's a 4, and so is this a 4. And you know, because it adds up to 16, this one's also going to be a 4. And then because this right here is the one underneath it, this one's going to be a 6. And then this one's going to be a 6, and this one's going to be a 4. So first shape is cracked. So we have that the kite shape for the octagon, like this kite, the angles for it are 4 pi over 8, 6 pi over 8, 4 pi over 8, and 2 pi over 8. Alright, first shape cracked. Alright, I'm going to use another marker. Maybe. I don't know. So 4, 6, we got a 6 here. And then we know that, well, we don't like know, but you know, it is something that comes up. I mean, just by looking at it, you might see that that sort of comes in and across. But it turns out that that angle is the same as this angle. And well, this one actually has a nice analysis to it. Like this angle right there is this angle right here. Right? This one. So that means that this angle is the same as that one. No, rather this one is the same as that one. Because it's like there. The bottom of this one. So this one is also a 6. Because the shape, this angle right there is this angle right here, so this one's also a 6. And so we're adding, this is also a hexagon, so we have to add up to 4 pi. So we're in base 8, like mod 8 if you will. So we have to add up to 4 pi because it's a hexagon. 4 pi, 4 times 8, that's 32. So 32 pi over 8 is equal to 4 pi. That means that this 32, we have to find this sum of 32. So we have 4 numbers of 6, and we're missing 2 that are the same. So we could say that there, so 6 plus 6, that's 18, plus 4, that's 22. So 22 plus twice of some number, let's call it x, is equal to 32. So, you know, pretty fast, like what number double makes 22 be 32? We find that x is equal to 5 because it's 10, what we're missing. So that means that x is equal to 5, so that means that the number we're looking for, this one has to be 5. So this hexagon that right there, that hexagon right there, has an angles of, I'm going to write them outside, 4, 6, 6, 5, 5, and 6. And we're also saying, well, this one is an interesting case. These 2 at the bottom are the same, and these 4 at the bottom are the same, but they're different. Because then it would just be a regular hexagon, wouldn't it? So I'm saying that these 1, 2, 3, and 4 are the same to themselves, and these 2 are different from them, but amongst themselves they are the same. So when you construct this hexagon, you got to be sure of that. You got to be sure that this edge and this edge are the same. And well, the angles will just come up. And it's interesting to think about because we see a number come in here, the 5. 5 pi over 8 is not on the number list. So if we write it down, we write that angle 5 pi over 8 down. I'm going to erase this for the hexagon. I'm going to also erase this little part of it. I think that we're only missing like the stars itself, and we're missing like this thing, but we can just like, you know, simplify, we can actually find the angles for it. So, what time is it? Okay, I need to be almost done, so what was I going to write? Oh yeah, this angle, the 5 pi over 8. So, it's not on the list. We see on the list only 6, 4, 2, and 0. 0 being just a line that crosses right through the center. 2 is the N3, 4 is the H2, A3, and this is just a polygon. So 5 has to be somewhere in between here. So between the A2 and the polygon itself, that's where this angle is. We multiply by 2 in order to get an even number on the numerator. And we get 10 pi over 16. Now this 10 pi, we get it when we subtract n minus 2k. So what are we subtracting from 16 to get 10? 6. 6 is twice of 3, so we're here in the n3. So that means that this one has to be, the angle comes from the 16/3. So we had 16 points and we did this process of jumping vertices. This is the star that will give us this angle. So we have a 16-fold angle, if you will, within this scheme of 8. It's a bisection. Of course, this is why we can still write it in 8 form and not have to go to 16-fold to explain it. But it's interesting to think that that angle right there pertains to this star. This angle right here pertains to this star. Which is interesting if you think about it, like, you know, like how they come together. I mean, I think it's pretty interesting. Like trying to visualize it. Yeah, it's a little over 90 degrees, you know. Actually, I'm gonna draw that in a while, just for fun. But yeah, so we cracked, you know, the thing for this. This one also has that where these two are the same, but these are different from that. And well, what's even interesting would be now to like do more of a geometric analysis and actually try to find the ratio between these like distances amongst themselves. And we could make a case that they are crackable. All right. So beyond the why I'm doing this, which is the answer is I don't know. We're just missing one more piece for that pattern. We have the kite. We have the hexagon. So now we get like, let's get this little squiggly guy, which is like a double star. So it kind of goes like that, goes like this, and then kind of copies like that, right? All right, so let's get that guy. So this angle comes in at the 8/3. So 8/3, that's a 2, so we have a 2 here, which makes it so that the angle inside is a 2. So maybe I should write it inside. Now I'm going to write it outside, but that's a 2. That's a 2, this a 2, this a 2, all of them are 2s. So the angle that comes in at that angle, that's a 2. Then what is this? Well, that's the point underneath of the hexagon. You see there, the point of that hexagon comes in there, so it has to be, so it's like this angle is 2 pi minus 4 pi over 8. So we're saying that it's like 2 pi minus 4 pi over 8. So we're going to make that into like common denominator, 16 pi over 8. So 16 minus 4, that is 12. So this angle on the inside is 12. 12 pi over 8. Like this whole angle right there, it's 12 pi over 8. And well, so it's going to be that one. That's also going to be a 12. So I don't know if I should write it inside or the outside because it might get confusing. I'm going to write it inside, and on the outside I'm going to write just 4. Maybe that will clear it up. 12, 2, 2, what is this? It's the bottom, no, the top, so that's a 5. So there's a 5, so same deal. 2 pi minus 5, so it's 16, that's an 11. So right here, there's an 11 pi over 12. So that's a 5, so that has to be an 11. Here an 11 as well, here 12 as well, 11, 2, 2, 5, 4, 5, 5, 11, 11, 2. And, interestingly enough, in this case, actually not all of them are the same. Because we're saying that these two at the bottom are the same, but they're not the same as the ones on the top. And the ones on the top make these. So we're saying that, you know, if we were to find different values for these things, interestingly enough, actually now that I'm looking at it, we should write them because these two at the bottom are the same as these two at the top. But these at the bottom are not the same as these on the top. So maybe we should write something else for these on the bottom here. So I'm just going to write 3 lines just to distinguish them from these on the top. So these right there are these. So that's 1. It's like the same line as that one, right? And then these inside are like that. And these are all the same to them. So yeah, that's the shape of that thing. This double looking thing. So, you know, we have all the angles. So what would happen if we sum them up actually? I don't know what would happen if we sum them all up. I've never actually analyzed like, well, what is the sum of these angles? So let's just look at it. I don't know why, let's just do it. So 2 plus 2, well, how many 2's are there? There's 6 2's. So that means that we have 12, right? So we have 12 pi plus 4 11ths, so that's a 44, plus 2 12s, so that's a 24. 12 plus 24, that's 36. 36 plus 44, that's 70, isn't it? Isn't it? No, it's 80. God damn, is it 80? Let's do it again. It is 80, man. It is 80. So 80 pi over 8, so that's 10 pi. So 10 pi, we could look at it as 12. So how many points does this thing has? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Well, goddamn, this has 12 points. So the sum of the internal angles has to be equal to 10 pi. Ain't that a bitch? Ain't that interesting, man? That's fascinating. I didn't know that. That's so cool. Because there's a 12-pointed polygon, the sum of the internal angles will be equal to 10 pi. And it is. We've summed up all the angles, and there you go, 10 pi. Beautiful. Man, I love this shit, man. This is fascinating. I love it, man. This is why, I don't know, this gets me a kick. How are we doing on time? Yeah, no, we're done for today. So, yeah, we'll leave it at that for now. So, yeah, do the list. Enjoy, have fun. And, remember that. That's a cool one. Recently discovered yesterday. I might do a book on this every now and again. I don't know, shit. Little devil. And yeah, hope you enjoyed it. Hope you had some fun. And yeah, I'll catch you in the next one. And pretty much I think all I have for now. So see you guys. We have a question here. Oh, so satisfying, somebody said. Who said it? Waisa Sahid's amazing class, of satisfying. Thank you very much. So, right on. Leave it at that. We have a quote there on the corner there. The harmony of the world is made manifest in form and number by the RCWT. So yeah, take care, guys.